In the last video, we talked about the law of reflection, or what happens when a ray of light bounces off of an object. Well, what happens if it doesn't bounce off an object? What happens if it goes through that object? Like, for instance, glass or clear plastic. Water, for instance. Well, we have what's called the law of refraction, which is also known as Snell's law in a lot of other physics textbooks. So, light bends as it goes through medium of different, what's called an index of refraction. Light travels at the speed of light, which again is 299,792,458 meters per second. Kind of interestingly, your book actually goofs up on that number. It leaves out the 9. If you look at the number your book gives in 2 different locations in this chapter, I'll email them to see if they can correct it. Still, they give the right approximation, 3 times 10 to the 8 meters per second in a vacuum. So when there's no material, when space is void, no air, nothing, light travels at this speed. But when you add material, like air, or water, or glass, then the speed of light is diminished. Light travels more slowly through these other mediums. However, once it leaves the medium, it speeds back up. So light travels at a fixed speed in water. And when it leaves that water, it travels at whatever the speed is in the medium that it leaves. So if it starts off in air, goes to water, and then ends up in air, the speed of light is the speed of light in air, then the speed of light in water, then the speed of light in air. There's no acceleration that you have to worry about or anything like that. The light travels at whatever speed it travels in that medium. Well, how do we know what the speed is? Well, we actually have ways of measuring that, and we'll measure it with what's called the index of refraction. Now, refraction is a term like reflection that talks about the behavior of light in a medium. Refraction is the apparent bending of light. It's the redirection of a light ray as it goes through a different medium. And that redirection can cause some silly and interesting effects. I'll put up a figure here where, like in a swimming pool, if you're looking at a person above water and then some of the person below water, it can look like that person's head is detached from their body or that they're much shorter than they are normally. If you have an aquarium, you know that as you move around the aquarium, the fish appear to be in different locations depending on which side you look at, because light bends when it goes through water and when it goes through glass. The amount that light bends depends on that speed difference. How quickly does light travel in that medium versus how quickly does it travel in a vacuum? That ratio is called the index of refraction, and the symbol we use in this chapter is just a lowercase n. So n is the index of refraction. It is simply the ratio of the speed of light in a vacuum, which is a constant, divided by the speed of light in that material, whatever that material is. So if you know what the speed of light is in the vacuum, which of course we all know, it's this value here. If you know what the speed of light is in the material, you can calculate what the index of refraction of that material is. Or if you know what the index of refraction of the material is, you can tell me what the speed of light is in that material. Now, some examples for common things that light travels through in your everyday life where you will need to know the index of refraction to solve the problems in this chapter. Remember, the index of refraction for a vacuum is 1, right? This number can never be smaller than 1. The speed of light in a vacuum is the fastest light can travel. So if the speed in a vacuum, and then the medium you're in is a vacuum, so it's C over C, that's equal to 1. So the index of refraction in a vacuum is 1. For every other speed, it's going to be smaller than the speed of light, so this fraction will always be greater than 1. For air, it's very close to 1. In fact, we will use 1. You can use the index of refraction as 1 when we're talking about a ray of light in air, because out to 4 significant digits, it's equivalent to 1. It is a little bit slower, right? It has a higher index of refraction, so the speed of light's a little bit lower in air. And it can also vary in air, depending on the density of the air, right? Air can be a different temperature. Air can be different and therefore have different densities. An example would be if you've ever looked at the air over a hot grill, right? You know that the air shimmers. And if you're looking through that hot air coming off of a grill or a hot road, the air coming off of a hot black paved road. That shimmering effect is due to the different index of refraction of the different temperature air in that heat flow, basically. Another example is if you've ever looked out in the night sky and you've seen the stars twinkle. Well, the stars don't twinkle. They're giant balls of hot plasma trillions of miles away. But what you're seeing is the light bending slightly as it goes through our atmosphere, because our atmosphere, the air is at different temperatures. So we get that twinkle effect. The more turbulent the atmosphere, the greater that twinkle effect. So for an astronomer like myself, that's very annoying. We want to find areas to place telescopes where the seeing, where that twinkle effect is very minimal. So water. Okay, fresh water has an index of refraction of around 1.3. Glass. There are different types of glass depending on what it's comprised of. Different types of glass have slightly different index of refraction. Diamond has a very high index of refraction, around 2.4. That's one of the reasons diamond becomes as sparkly as it does and why it's so sought after as a jewel, because it has a very high index of refraction. So when you cut all those different facets in a diamond, you can get a lot of internal reflections in the diamond, causing the diamond to really sparkle. If you have a piece of glass the exact same shape as a diamond, it will not sparkle like a diamond will, because glass has a much smaller index of refraction than diamond. You might have heard of cubic zirconia as a type. That has an index of refraction of 1.8, 1.9. So it's closer to diamond, but still not quite there. So once we know what the index of refraction is in a material, we can use that knowledge to talk about how a ray will bend as it goes through that material. So now that we know what the index of refraction is and what it measures, we can look at how that index of refraction is needed when calculating what's called the law of refraction. So the law of refraction is basically, how do we know how much a light ray bends when it enters a material or medium of a different index of refraction? So it's not as simple as the law of reflection was. The law of refraction states that the index of refraction of material 1 times the sine of the angle as measured from the normal in material 1 is equal to the index of refraction of material 2 times the sine of the angle as measured again from the normal of that ray from the normal in material 2. So, for example, here is basically air above water. So think of it like a pond. You have some air sitting on top of some water. This line here, we'll call the interface. That's just the boundary between the air and the water below. So here we have a laser pointer, again, a light ray coming in at some angle. We're going to call air here, that material we're going to call material 1. That's where our ray originates in the first material. And we're going to call the second material, which happens to be water. This could be glass or diamond or whatever. We're going to call that material N2. So theta 1 is the angle measured in material N1. Theta 2 is the angle measured in material N2. If I know what this incident angle is, let's say it's 45 degrees, and I know what these index of refractions are, and I do, N1 for air is approximately 1, N2 for water, for fresh water, is 1.33. I can calculate then what this refracted angle is. Again, measured from the normal. So we draw a dotted line where the ray intersects the interface, normal to the surface. Both angles are measured from that normal. But again, like reflection, they're on opposite sides. So the angle of incidence coming in, if this material had the exact same index of refraction, that ray would continue on in a straight line. But it doesn't. So we can use this equation, plug in the known values. So n1 is 1.0 times the sine of 45 degrees is equal to 1.33 times the sine of our unknown angle theta 2. And all of you have the math skills to be able to solve for that unknown angle. Just remember that your calculator has to be in degrees mode for this, for you to get degrees out when you take the inverse side of this function. When you solve that for theta 2 and then take the inverse side. If it's in radian mode, you'll get radians out, which you can convert to degrees, but just make sure you know what numbers you're getting out of your calculator. Now, when you go from a low index of refraction material to a higher index of refraction material, the ray bends towards the normal. The opposite is true if you go from a high index of refraction material to a lower index of refraction material. So here's the same interface, same materials, but now I'm underwater shining a ray upward. Imagine I have a little waterproof laser pointer. I go under the water and I aim it upwards. Here is my first angle. Water is now, measure n1. Air is now n2. This is my angle, refracted, bent angle, theta 2. If this were water-to-water interface, the ray would travel in a straight line. But because we're going from a high index of refraction material, 1.33, to a low index of refraction material, 1.0, the ray bends away from the normal. So when a ray of light enters a medium with a lower index of refraction material, the ray bends away from the normal. When it enters a medium of a higher index of refraction material, it bends towards the normal. How much it bends depends upon the ratio of those index of refractions. Using this equation, this again is often referred to as Snell's law. Your book calls it the law of refraction. You use this equation to determine how much a ray of light is bent when it enters a different medium. Again, you have to measure those angles from the normal. Just like for the law of reflection, you need to know where the normal is for the interface in order to measure the angles from the normal. You do not measure the angles from the horizontal. You measure them from the normal, from the vertical, compared to the surface. If the surface is horizontal, the normal will be vertical. So as you can see here, the ray of light bends away from the normal if you go from a high index to a low index of refraction material. But if I keep on bending this at a greater and greater angle, eventually the ray that comes out will be at 90 degrees. What happens if I continue to increase this angle? Well, then the ray will come out at greater than 90 degrees, but that really can't happen. That process is called total internal reflection, and we'll be looking at that in the next video.